Good morning, students. So let's just discuss yesterday's topic first. So it was encoder and decoder. So basically, have you understood these encoders and decoders? Basically, this encoder is a combinational circuit that converts the binary information in the form of 2 raised to power n input lines, okay, into n output lines that represents the n bit code for the input. Okay, for like if we have 2 raised to power 3 means 8 input lines are there. If 8 input lines are there, so 8 when converted to 2 raised to power n form, here 3, so that means n is equal to 3. So for every input given in this 8 inputs, we will give the code into 3 bit code. So that means these input lines will be converted to n bit code. And what is the n? N is the number of inputs given when converted to 2 raised to power n form. That will be the n number of output lines. Means from this n we will decide that how many outputs will be there. For simple encoder, it is assumed that only one input line is active at a time. Means at a time only one line is active. Like if D0 is active, here all the values are 0, 0 and 0. Okay. So if this D5 is active, this line is active, it will become 1, 0 and 1. So 4 and 1, 5. Similarly for 2, it will become 0, 1 and 0. So this is the octal to binary encoder. So as shown in octal to binary encoder is that we will take 8 input lines and give the result in binary form of 3 output lines. Clear? Next, we will see the truth table of this encoder. So it is just the representation that we have discussed, that we will start it from D0, this D0 to D7, and see in this case the it is very easy to remember that just write down D0 to D7 and the one, just put one in a diagonal form like this. Okay, rest all the places are 0. And second thing is that to represent the x, y, and just write down first x, y, and z, and then convert this value. One second. Convert this digit, the digit that is associated with the D, it is 0, 1, 2, or 3 up to 7. So convert that into the 3 bit form. Okay. So for 0, we will have all are 0. For 1, we will have 0, 0, and 1, because this is 2 raised to power 0, 2 raised to power 1, and 2 raised to power 2. Okay. So for 2, we will have 0, 1, and 0. Similarly, for 5, we will have is 1, 0, and 1. And at last 7, we have 1, 1, and 1. Clear? Okay. So now see, as truth table, the output is 0, 0, 0, 0 when D0 is active, and 0, 0, 1 when D1 is active. So that means only one line will active from this side. So this 1 means, and the whole 0 means, what does that mean? that now suppose if we consider this table or this line, here one means only this D3 line is active at a time, rest all are inactive, and for this we are getting the result 0 1 1. Clear? And next is decoder, that will do opposite of the encoder. So decoder does the opposite job of encoder. It is a combinational circuit that converts the n lines of input into 2 raised to power n lines of output. So in this we will have given 3 input lines and we will convert it into 2 raised to power 3 form, or we have n output lines, n input lines, and we will convert it to 2 raised to power n form. Clear? So it is the binary to octal decoder. So 3 to 8 line decoder is there. So D0 is high when X is 0, Y is 0, and Z is 0. So in this we will represent X bar, Y bar, and Z bar. Okay. So see if it is 0, 0, and 0. Here we are using the AND function. So AND means if any one is 0, so the whole value will be 0. So in that case, it will be supplied over here to this one. Now the line will be activated up to this point. Okay. So it is 0. So when it is taken complement, we have 1 here, 1, and here 1. Okay. So this D0 will get clear. And next we will have the truth table of this decoder. So simply it is also the vice versa of this decoder. We will write down first X, Y, and Z. Okay, so it will be from 0, 0, 0 to 1, 1, 1. And now see here in this, again the diagonal form is 1, 1, 1. Just write down D0, D0 to D7. Okay, and just write down 1 1 1 diagonally, and rest all the places are 0. Again that means that out of D0 to D0 to D7 only this line is currently active, rest all are inactive. Okay. Clear? Now we have discussed that combinational logic circuits. So what are they? Let's just discuss first. What are the combinational logic circuits? So these combinational circuits are designed by using the IC chips. So these IC chips are using the packet density. That density will be decided according to the gates that is being used in the chips. So first is small scale integration, in which up to 12 gates are used. Then MSI is there, medium scale integration, 12 to 99 gates are there. Similarly, then LSI, 100 to 10,000 gates, less than 10,000 gates. Very large scale VLSI, 10,000 to 1 less than 1 lakh gates. And then we have ultra large scale integration, greater than 1 lakh gates. So main objective of this circuit design is to reduce the number of gates for SSI circuits, reduce IC package for complex circuits, increase the speed, as well as the design should be simple. So this is the application of CLC. This is used for arithmetic and logical function, data transmission, code converters. In arithmetic logical function, we will use the adders, subtractors, comparators, parity level decoders. Then data transmission, we have multiplexers, demultiplexers, and coders, decoders. Then code converters are there, binary, BCD, 7 segment. Have you done the 7 segment decoder in DE? Anyone remember? Okay, so we will discuss it. Display device है जो that is in your used in your calculators, that is called the display 7 segment decoder. So the logical circuits are basically of two types: combinational and sequential circuits. So combination logical circuits, these are without a memory. So all the gates and all the circuits that we have discussed till now is a combination circuit. So in this type of logical circuit, output depends only upon the current inputs. Till the time we have the current input, we are getting the results. As soon as we will switch off the circuit, and all the data will be gone. So then we have the sequential logical circuits that are there with memory, and in this type of logical circuit, output depends upon the current inputs. So we do need the current inputs to execute the or to implement some operations over the circuit. Yes, but it is able to store the previous results. So like counters are there, flip flops are there. These are all the sequential logical circuits. So combination logical circuit, basically it consists of the input variables, logic gates, and output variables. For n input variables, basically we have 2 raised to power n possible combinations of binary input that we already discussed in the encoders. For each possible input combination, there is one and only one possible output combination. So, and also the combination circuit can be described by Boolean functions for each output variable. So every input should be expressed in terms of the n input variables. So this is the design procedures. Just read it once. It is not as important as in your syllabus because it is already covered in the digital electronics. So the next topic is binary address. So the digital computers perform a variety of information processing tasks. Among the basic functions and counter are the various arithmetic addition and okay. So in binary address, we will implement the addition operation. Till now, we have discussed that do not get confused about the logical gates as well as the binary address, because in OR gate, if we use 1 plus 1 or 1 or 1, it will become 1. But when we use in binary address, the results will become different. So in binary address, these are the cases 1, 2, and 3, 4, and the cases depends upon the number of variables given. Like in this, we have two variables given, A and B. So the method is same, that we will see how many cases are there. It depends upon the n. So n is 2. So that means 2 raised to power. So that means 2 raised to power n is 4 cases should be there. If we have n equal to 3, that means 2 raised to power 3 is equal to 8 cases will be given. Okay, 8 cases will be there. So here a plus b, so 0 plus 0 is, here we have two outputs. Till now we have only single output, but in these binary adders and subtractors we will have the two outputs. In adders we have sum and carry. In subtraction we have difference and borrow. Clear? So sum is sum and carry are there. So see, for 0 and 0 we will have sum is 0 and carry is also 0. For 0 and 1, sum is 1, carry is 0. No carry should be there. For 1 and 0, sum is again 1 and carry 0. But at last step, we have sum 1, carry 1. So it will become sum is 0, but carry is 1. Clear? So if we write down 1 and 1, it will become 0 and carry should be there. If no digit is there, suppose it is 0 and 0, 1 and 0, 1. So then it will become 1 and 1. So it will become 1, 0. But if no digit is given over here, no digit is given over here, then it should be vanished off, so that it will become the 0. Up to this point, is everything clear to you? Yes. Okay. So now see, if we analyze this part, sum part, oh, one second. If we analyze this part, sum, which gate is being implemented over here now? Do you remember that 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, and 1 plus 1 is 0. So that means XOR gate is being implemented over here. So we have, okay, I will write at a different place. So sum S is equal to A XOR B. Clear? And if we see this part, the carry part, which gate is being looks like this? 0 and 0 is 0, 0 1 is 0, 1 0 is 0, and 1 1 is 1. So that means this carry C is equal to A and B. Clear? So then we have the half adder. So that we have already discussed that half adder is only 2 bits are used and 2 bits are the outputs, and sum and carry are the bits, and A and B are the 2 input bits. So logical expression sum is equal to A XOR B, that we have already discussed, and carry is equal to A and B. And the circuit of this half adder is AB This is the XOR gate, and this is the AND gate. It is being implemented, and this is the truth table of this half adder. Clear? Okay, so now this is it for the today's lecture.